So first of all, thanks very much for the opportunity to speak, and also for the kind invitation to stay here at the Institute this week. So I will be talking about some recent joint work with Rui Han from UC Irvine, and as I learned, he will be here next year. And in this work, we were interested in quantifying the large coupling behavior for the Lyapunov exponent of quasi-periodic Schrödinger operators. So morally, we were interested in the regime of localization for such operators. And it's a particular pleasure to be talking about this work here because this is a continuation of a result that Tom Spencer and Eugene Soretz obtained in 1991. And I will talk about this as we go along. A while ago. So maybe let me start with a little bit discussing the setup. So I'm interested in a quasi-periodic Schrödinger operator, which is a family of discrete 1D Schrödinger operators. And this family is indexed by points on the one-dimensional torus, or the unit circle if you want. And this variable x that indexes the members is usually called the phase variable. And for each member, you get a 1D discrete Schrödinger operator, which has the usual form. So you have discrete Laplacian, like here. And then you have a multiplication operator, which is called the potential. So the word quasi-periodic pertains to the fact how this potential sequence is generated. So I should explain there are two ingredients here. So one ingredient is an irrational number, which is denoted here by alpha, which is usually called the frequency. And this irrational number generates some base dynamics. So what we want to do is we want to look at the unit circle. And then we look at a particular member in this family, and that corresponds to a point here. And then what you do is you rotate this point repeatedly by alpha, and thus you generate a rotational trajectory. And then what happens is there is a second ingredient here, which is a function f. We'll assume this function to be analytic on the torus and real valued, so that this is a self-adjoint operator. And then what you do is you just take this function and evaluate this along this rotational trajectory, and thus you generate this potential sequence. And you do this for each x, so you get this family, and that's a quasi-periodic Schrödinger operator. Quasi-periodic because if alpha was rational, this would be periodic, but our alpha is irrational, so we get a quasi-periodic operator. And we will be interested in being able to modulate the relative strength between the discrete Laplacian and the potential. And the way that I want to do this is by including here a lambda. So that's the coupling. So lambda is a real parameter. And that modulates this relative strength that will be interesting for us. And we will be particularly interested in the regime where lambda is large. Now, maybe I should say a couple of words about the context that these operators arise in physics. If you had not seen this type of operator before, then you could come to the conclusion that this setup is rather artificial. But it turns out that these operators naturally arise in solid-state physics when describing the effects that an external magnetic field has on the electrons of a two-dimensional crystal layer. So you have a magnetic field that's perpendicular to this crystal layer. And in this context, alpha, the number by which we rotate, represents the flux per unit cell. And then if you assume a Bloch wave in one direction of the lattice plane, and this Bloch wave has quasi-momentum x, then the conductivity properties in the transversal direction of that lattice plane are governed by such an operator. So that's the context. And one phenomenon that is interesting here is our metal insulator transitions that are triggered by varying this parameter lambda. And that's what we want to understand. So, I mean, purely heuristically, right? What could you expect? So if lambda is less than 1, then you would say, okay, that means that the Laplacian will dominate the potential, and so you would expect that you have delocalization, so your wave functions have block wave form, something like that. On the other hand, if lambda is comparatively large, then the potential energy will dominate, so you expect to have localization, so your wave function will exhibit some exponential decay with some decay rate, which of course corresponds to the inverse localization length for this particle. And we will be interested in this regime. And what I want to do is I want to make this rigorous. So this heuristics, the goal is to make this rigorous by saying something about this L. In order to do that, one way to look at these delocalization-localization transitions is to quantify this L by introducing the so-called Lyapunov exponent. So let me say a couple words. So Lyapunov exponent, loosely speaking, tells you something about the asymptotics for solutions to the time-independent Schrödinger equation that is associated with this operator. So if you look at these solutions, because this Hx is a finite difference operator, of course you can generate those solutions iteratively, right? Using transfer matrices. So say you specify an initial condition at point 0 and -1, then you get a solution at n -1 by applying certain matrices or a product of matrices. It's usually called the n-step transfer matrix. So this is a 2x2 matrix. And this 2x2 matrix is generated as a product of matrices that sort of mimics what goes on for the potential here, right? So potential was generated by evaluating a scalar function along this trajectory. So what we'll do here is we'll take a matrix valued function, which will be this. So E minus lambda f of x minus 1, 1, 0. And then what you do is you just, for the n-step transfer matrix, you take this matrix valued function, evaluate it along the trajectory up to n minus 1, and take a product. By this weird notation, what I just mean is that you multiply from here to here. So from right to left, which is for you from left to right.
So the order is very important.
The order is important, yes. And now this nice iterative scheme has a formulation as a dynamical system, which is called the Schrödinger cocycle. So the Schrödinger cocycle it's a dynamical system. I will denote it by this pair because these are the two ingredients, right? You have the frequency and you have this matrix valued function. And it's a dynamical system that acts on torus cross C2. And it's a linear skew product that the way that it works is the following. So the first entry, which is a point on here, just keeps track of the base dynamics. So you rotate by alpha. The second entry, which is a vector in C2, generates exactly the solutions to this iterative procedure. So if you iterate this, then you get exactly what you wrote here. And now, associated with this dynamical system, as with any dynamical system, you can look at the asymptotics, and in particular, you can introduce the Lyapunov exponent. So Lyapunov exponent is then defined. So you look at the growth of the n-step transfer matrix. This double bar denotes any norm. There is an x dependence, and I want to average over x. And then take the limit as n tends to infinity. And it's not difficult to see that this is really a non-negative finite quantity. So in particular, you can think of this as a length, as an inverse localization length. So that should correspond to this thing here, to this L. And hence, there are two situations. Either the Lyapunov exponent is 0, which inverse means delocalization, heuristically speaking, or the Lyapunov exponent is positive, which then heuristically should tell you that you have localization. In fact, positive Lyapunov exponent is a necessary condition for localization. To say something about the opposite direction, you'll actually have to do some work. Nevertheless, this is the ingredient that you need. So that's why it's interesting to obtain statements about positivity of the Lyapunov exponent. And so that allows me to formulate the main result. And what this main result does is it gives a formula for the Lyapunov exponent as a function of lambda, at least in the large coupling regime. And it looks the following. So this formula, first of all, it will hold after some threshold, which I call lambda naught. So there exists some threshold lambda naught, which only depends on the properties of f and is not dependent on this frequency alpha. So that the Lyapunov exponent has the following behavior. So you have log lambda plus, then there is some logarithmic integral, which essentially has to do with this upper left entry. And then there is some arrow term, and we quantify this arrow term. So the decay rate is like lambda to the power minus 2 over 2 n plus 1. And I need to tell you what the n is. So the n is some integer, natural number, that also only depends on f. And this holds for all energies. And I didn't say anything about the frequency, so this works for any frequency, irrational frequency. So what that in particular means is if lambda is sufficiently large, right, then you have in particular positivity of the Lyapunov exponent, and you see that Lyapunov exponent behaves like log lambda in the large regime. And I didn't write this, so right there it should say if lambda is greater than or equal to lambda naught. Yes.
Do you know what n is?
And I was going to say something. So we can quantify all these parameters. So let me actually do that. So let's start with n. So n tells you something about the number of zeros of this family. Thinking of this as a parameter family. Parameter is e over lambda on the neighborhood where it extends to analytically. So what I mean by this, suppose f extends analytically to a strip of width h. Right, so h minus h, so it extends to a neighborhood of this strip. Then what you can do is you can look at the number of zeros of e over lambda minus f on this horizontal strip. And then you take a max over all e over lambda. And then this defines this n. So it tells you something about the number of zeros of this parameter family globally over this parameter. And defining n like this, lambda naught is 2 to the 2n plus 1. And 2 here will have some significance that I will be talking about. And yeah.
So the smaller h you take, the better you can get n, or what?
Well, if h is smaller, then n will correspondingly be smaller.
But I mean, which means that why don't you just take h equals 0?
But you can't take h equals to 0.
Well,
You can make it smaller,
so
yes.
you claim that you can make n arbitrarily small in general.
Yes. But then the error
But
term
you
will.
don't make large.
Yes.
Oh, I see.
Yes.
Also, another question: can you quantify the O capital?
Yes. So there is. So what I mean by this is bounded above and below by a constant, and we can explicitly compute the constant. I think it's 8. I don't know. Yeah, I think it's 8. But
So maybe I should ask Pierre, do you understand what the issue is here, or what the constructor is? Because Pierre, of course, studies localization from another perspective, but this is very different. But do you have any questions? Because it's all on the board here, so but it may not be.
Eigenfunctions.
Yeah, so localization means the eigenfunctions decay exponentially in this range, and in the case for lambda small, you're going to have these sort of plane wave type solutions. And there's a transition, which is quite interesting, which he's not going to discuss.
I'm not talking about the transition yet.
So right now he's just computing the growth of the solution as you, from initial value, growth of the initial solution as you go to infinity, and that's very important. That's the Lyapunov exponent, and he's getting good quantitative estimates on that, which will tell you what the localization length is, roughly speaking. I mean, this problem with Lyapunov exponents is a big problem. We understand it for these things, but for example, for nonlinear systems or for other skew shifts, we have very little understanding of it. In general, just product 2 by 2 matrices, but it's a tough question in general. Very tough question.
Can we come back to Ellie's question? Don't you want n to be small?
Yeah, that's just about something I wanted to ask. Yeah.
It's better if n is small, right? The error term is less smaller, and the lambda 0 is smaller.
Well, but you cannot get as small as possible, because since you maximize over lambda, if there is 1 0 somewhere, you will.
So maybe let me come back to this question. Yeah. So maybe let me come back to this question. So I should probably, since there was a history mentioned, embed this in the context of what had been done. And so the earliest, so I will only be talking about the situation where f is in the analytic category and doesn't have lower regularity. For this type of problem, the earliest results actually go back to Sorensen Spencer and Michel Herman. So Herman looked at a case where f is a trigonometric polynomial, and Sorensen Spencer needed to devise a different strategy to actually talk about the case that f is an analytic function. So one couldn't use a simple approximation argument to extend that. And what they obtained was a lower bound for the Lyapunov exponent. So they obtained a lower bound, and the lower bound looked like this. So lambda naught is this threshold. C is also only a constant that depends on the function. So that already tells you that for sufficiently large lambda, you have positivity and that you have a growth of that form log lambda. And then there were various generalizations of this. So let me just mention a few. So Bourgain, in his monograph on lattice Schrödinger operators, he gave an alternative proof of this lower bound, where he used some harmonic measure estimates to shorten the argument. Then should probably mention Zheng Zhang in 2012. So he extended this formula to the unitary analog of quasi-periodic Schrödinger operators. And then Duarte-Klein in 2014, they proved a formula like this for long-range Schrödinger operators. So that means Schrödinger operators on the strip. And in fact, a more recent result by Duarte and Klein was the motivation for our work. So Duarte-Klein have a paper on the archive from 2015. And they prove a similar formula for the Lyapunov exponent with similar, but there were certain differences. And the differences were the following. So first of all, they obtain a formula like this as an application of an abstract continuity theorem for the Lyapunov exponent. So they prove an abstract continuity theorem, and as their main application, they obtain this formula. But because of their strategy of proof, first of all, they had to assume that alpha is a Diophantine number. So there was a Diophantine condition which takes away a zero measure set of irrational numbers. So Diophantine in their case was just that if you look at the rotational trajectory and you measure the distance from the origin, then you're always a controlled amount away from the origin, and this is the control. So kappa is positive and r is less than 1. And so they had to impose this condition. But because they imposed this condition, their threshold, lambda naught, also depended on the Diophantine properties. It depended on kappa. And finally, this error term here, which is of Hölder form, is weaker in their case. So they have a weak Hölder error term. By this I mean an error term of this form e to the minus c log of lambda to some power. And this power is positive and less than 1. So if power was equal to 1, then this would just be a Hölder behavior. But they, because their modulus of continuity for the Lyapunov exponent is weak Hölder that they obtained, they also only got this weak Hölder dependence here. So what we do is we strengthen their result by first of all extending the result to all irrational frequencies and remove the dependence here, but also strengthen the error term from weak Hölder to Hölder. Now, one remark that I want to make is that the Duarte-Klein work also works for rotations on a higher dimensional torus. Our result strictly is one-dimensional. And that has to do, and you will see this, that we use niceties of analytic functions of one variables. By that, I specifically mean that the zero set is isolated, which is not the case anymore in several variables, of course. So their result holds from that point of view in a greater generality. Nevertheless, in the one-dimensional case, we can improve it.
So is this a fairly heavy analysis that they do? Or not?
Yes, that's a heavy analysis. Yeah, because again, they are not. They first proved this abstract continuity theorem for the Lyapunov exponent of cocycles, which are never invertible. They're nowhere invertible, and there's an application of that they obtain this.
Is this Pedro Duarte?
This is Pedro Duarte, yes. Yes.
Klein, is that what Klein?
No, it's Silvius Klein.
Oh, this is Silvius.
This is Silvius, yeah. Yeah, I should say actually. Yeah, I should have said.
Oh, Silvius Klein is good too, right?
Yes.
Pedro Duarte, I know he's working in dynamical systems.
Yes. Yes, and so it was a result of I think several papers where they looked at where they looked at continuity of the Lyapunov exponent in a much more general setting than irrational rotations. And one of the outcomes of this work was that also. Yeah. Okay. So maybe.
I guess there's one other comment you can make if I have it correct.
Yes.
I learned this from Ilya, which is that in the specific case where you take the cosine, then you have some identity, right?
Yes. Yes. So for specific models, for instance, if f, I called it here, f is the cosine function, then that's called the almost mature operator. And in this case, you actually have this identity, right? So it's actually equal to log lambda, max of log lambda and 1.
And if I put your f, if I put that in your formula, does that
on the spectrum,
see
yeah.
that canceling out, or how does that work?
No, it does not quite come out. Yeah, but we know. I mean, let me say it like this. So the technique that we are using is can be used also to get the exact formula for the Harper's model. Yes, yes.
So same technique, but
yes,
maybe
because it's basically it uses complexification in the phase variable, which is what I will be talking about. Yeah.
Does it mean the second term for the almost mature case is just 0?
It's 0. Yes.
Okay.
Yes.
Okay.
Yeah.
Infinite, wouldn't it?
No.
If you had a cosine in there.
It's 2.
Oh, it's 2. Oh, yeah.
It's level set always set.
then there's no error. I mean,
But there's no error.
There's no error at all. So it's an interesting case, right?
Yes.
It's probably amazing that you get the exact formula.
Yes. There are also other models where you can get an exact formula, but they're all of degree 1. That's the deal here, because that sort of restricts the possibilities that you can have. Yeah.
Isn't it cosine for the almost mature?
Yes.
Because you have cosine and alpha, so that's quasi-periodic on the lattice.
But the level sets of cosine are.
But there is no error term.
Oh, okay. Yeah, well, okay. But if you plugged in that formula for the thing, you would get n equals infinity, right?
Why is n infinity?
Because the number of roots of cosine minus, say cosine minus 0.
So you choose a fixed h, right? Then the number of roots is given by the degree.
This has real roots, so it doesn't depend on h.
Yes, and that's 2.
2.
It's degree 1, so it has 2 roots.
But doesn't cosine have an infinite number of roots?
On the torus.
Oh, it's torus.
Yes, between 0 and 1.
On the
Right.
complex torus, so it's like z plus 1 over
Yes.
z plus 1 over z. Think about it on
So this t is r mod z. And then you look at extensions of that. Okay. So let me maybe explain an outline of the argument. So and the first step really goes back to the idea of Soritz and Spencer, and that is the following. So remember this matrix valued function that generates solutions and that gives rise to the Lyapunov exponent looks like this. And I'm taking the lambda dependence explicitly out because I want to think of this as large eventually, right? And so the idea of Soritz and Spencer was to somehow argue that this upper left entry dominates for large lambda, but there are certain obstructions here because, of course, this has real zeros, right? This argument here. And so naturally, because f is analytic, you try to avoid the zeros by extending to the complex plane in X. So the first step here is to complexify the dynamics. And what I mean by this is complexify in X. So what you do is you look at a cocycle where you extend to the complex plane, and the complexification parameter is y. So that's the imaginary part. And for fixed energy, I want to think of this as a function of this parameter y. So I want to think of y as a parameter. And of course, eventually we're interested in putting y to 0, but y will help us in the argument. So associated with this, you have Lyapunov exponent, which again, for fixed energy, I want to think of as a function of y. And now, okay, so now you extend to the complex plane, and it's clear that if you do that, you can avoid zeros uniformly over x. So you can bound this below, but you want also, remember, we want to be able to vary lambda. So we want that this uniform bound below, this eta, can also be chosen uniformly in E over lambda. So we need eta uniform in E over lambda. So that will be the first ingredient, and I'm putting lemma on the quotation mark because I will have to say something about this. So basically you pay a price, right? Because you want eta uniform in this parameter, the price will be that the height at which this occurs will depend on E over lambda. So the bound will not, but the height will. And I will formulate this precisely later. But once you have this, right, what you can do is you can factor out the upper left entry. So you have that this upper left entry now is bounded by lambda times eta, which is positive, so I can take it out. And then I'm left with the remainder. So the remainder has the form 1, and then you have 1 over this thing, which will be small as lambda gets large. And then a similar term and 0. And again, this is meant in the limit as lambda goes to infinity. So what this tells you is that this remainder that you have is close to a constant cocycle, namely to this matrix 1, 0, 0, 0. So you have a limiting cocycle that is determined by, that is a constant, and it's not difficult to see that the Lyapunov exponent for a constant is just the log of the largest eigenvalue, so in this case 0. So what that means is that you get a formula for this Lyapunov exponent of the real axis of exactly the form that we want. So you get the Lyapunov exponent is the logarithmic integral of this prefactor, so which is just log lambda plus this integral of the log of E over lambda minus f, but at this height y. And then you somehow have deviations from this limiting cocycle. So there will be an error term. But of course, this argument is only rigorous if you have two things. One is continuity locally of the Lyapunov exponent of this remainder locally about this limit cocycle. And the second is you need a modulus of continuity. And so that's the second ingredient. So lemma 2, and again, I'm not formulated precisely here, but I'll do this later. So modulus of continuity about this limiting cocycle. And so that leaves us with our result, but off the real axis, if you believe that. And so step 2 is then, of course, to somehow argue that the same formula persists as you take y to 0. So you want to extrapolate to y equals 0.
It seems like a ridiculous thing to do, to go off the axis, where you can see everything is fairly easy, but then this mnemonic trick shows you how to get back on.
Yes.
subharmonic.
Yes, and you had to develop another trick, which was this extension of Jensen's formula, and we will not precisely use this, but somehow something that underlies this, and this is convexity. So let me explain. So I want to extrapolate to y equals 0, and the key for this is to use the fact that if you look at this Lyapunov exponent for fixed energy, depending on y, then this function is a convex function in y. In y, yes. So for fixed energy, the claim is that this is convex in y. And that's what we use, yeah. And this was known before. This became clear in Avila's work on quasi-periodic operators. And it's actually not difficult to see, so let me briefly explain. So it just goes back to the definition of the Lyapunov exponent, because if you remember, Lyapunov exponent was defined in this way. You have the n-step transform matrices. Now we complexify it in the phase. So I want to argue that this is convex in y. Of course, it's enough to do this for each element, for all the elements of the sequence. But then once you look at the fixed n, right, you have the log of the norm of something analytic. So that is subharmonic. So what you're dealing with is the average of a subharmonic function for fixed heights. And then there is this standard fact from the theory of HP functions, which I think usually is associated with Hardy, which just says that if you have a subharmonic function on a horizontal strip, and you look at averages of this subharmonic function for fixed height, then this function is convex. And that's what implies that in particular this is convex. So we have convexity, and so the tool to do this extrapolation is actually to work with the right derivatives for this function. So it turns out that these right derivatives also, they played a role in Avila's work on the global theory of quasi-periodic Schrödinger operators, which was parts of his Fields medal work. So this right derivative with respect to y divided by 2 pi turns out that, and that's what Avila proved, only attains integer values. So you can think of this right derivative somehow like a winding number of the cocycle. So he called this acceleration. Let me call it omega. And so what we prove is we prove an upper bound on the acceleration. So this is lemma 3. And it just says that if you look at the acceleration at y equals 0, then this is bounded above by, so it's always non-negative, that's known, but it's bounded above by 1/2 times n, where n is the same n than before. And that holds, again, if lambda is greater than or equal to lambda naught, and for all e.
Your derivative is in y or?
The derivative is in y, yes. Yes, alpha is fixed. Yes, I'm sorry. Yes, should be the other way around. I'm sorry. Yeah. And I should say something about this because from this work of Avila's, it's clear that this acceleration encapsulates all the information about the spectral properties, about the quasi-periodic operator, if you know it at y equals 0. So from that context, this is actually interesting on its own that we can estimate this quantity. That
these have to do with, I mean, these must be related. The fact is, the other result, which I could know, I didn't know it. It has to do with the poles that I would see presumably when or the zeros that I would see when I do analytic continuation, or.
you mean the
The
fact
fact that that's quantized.
that this is quantized? Well, the way that I think about this is if the cocycle is the simplest type of cocycle, namely a diagonal, say the cocycle has this form, f0, 0, 0, right? Then the Lyapunov exponent is just log of integral of the log of f, right? And then, of course, the right derivative of this is just a zero counting function. So it's just the winding number itself. For this, if you think of this as a curve generated at fixed y in x, right? This traces out the curve, and that's nothing but the winding number about the origin. And so what he does is he proves this in general, even for cocycles that are not diagonal or cannot be changed to a diagonal cocycle. But that's why I was saying I'm thinking of this as a winding number, because yeah. Okay, so maybe let me comment a little specifically about these lemmas. And let me actually start with this modulus of continuity, which was lemma 2. So remember, the idea was that after taking out this large term, so it is over there, so lambda times this is large, then the remainder has this form, 1, something small, 0. So essentially, you have a form of this kind, so you have 1 over some function, 1 over the same function, 0. And this function is bounded away from 0. It's large. So let me call this uniform lower bound, let me call this little m.
So by the way, once I have lemma 2 and lemma 3, I'm done basically, right?
Yes, yes, yes. So
maybe you could just say how that works.
Oh, you want, okay.
I mean, it's probably pretty trivial.
Yes, so quickly, I mean, it's basically just an epsilon over 3 argument, right? So by convexity, so what you do is, right, so you have, I mean, the Lyapunov exponent doesn't look like this, because we know that it's actually a piecewise linear function, but you go off the real axis, right? And you have the formula off the real axis. But then on the other hand, you have a control on the right derivative. So you can sandwich it. You can sandwich it using this right derivative. So what I mean is, it's probably the easiest if I just write it down. So this is the, if I call this logarithmic integral, if I call this I, if I call this, we call this I of y. What I want to estimate is this. This is the Lyapunov exponent. These are the first two terms in my formula for y equals 0. And I want to show that this behaves like lambda to some negative power. And then you just you do this epsilon over 3 argument. You first look at the deviation of the Lyapunov exponent when you go to this height where you have a formula. This comes from the complexification. So you know that this you know that this function is convex in y. So you have, by lemma 3, you have control of this term. Then you have then you have the formula of the real axis. There is a log lambda. So this is the formula for the Lyapunov exponent of the real axis. And this is what we have here. And the claim is, because of this modulus of continuity, we have a good arrow term. And then there is the remainder, which is I of the difference between I at y, this integral at y, and the integral at 0. And this integral, as we just said over there, is essentially is also a convex function. So this integral itself is convex in y. It's essentially Jensen's formula. And you can easily estimate the right derivative of that. It will actually be controlled by the same n.
So where does lemma 3 come in?
So lemma 3 comes in here to control this term, because here we look at we use convexity of this Lyapunov exponent in y, so that uses lemma 3. Then lemma 1 and lemma 2 was obtained to prove a formula that holds off the real axis.
Okay.
And then this term is easy to deal with. So that's sort of the idea. But again, it's based.
I guess the picture is good, right?
Yeah.
The picture is helpful. And then you have to use the fact that you have this quantization of the winding number.
The quantization of the winding number I'm using here, because this is the step where you use that this function in y is convex, and you control this difference by the right derivative times y.
Good.
Yeah.
Thank you.
So maybe I can just formulate these two ingredients, and then I'm close to the end of time. So one ingredient, if you remember, had to do with the formula of the real axis, because we needed to have an error term here, and in particular make this continuity argument rigorous. And so that had to do with the remainder, with the cocycle of this form. G is, here we actually only need G to be continuous. It's some continuous function, and it's bounded away from 0. And you're looking at a matrix valued function of that form. And so what we show is, if this uniform lower bound is sufficiently large, and that means we show that if m is greater than 2, so if this uniform bound on this function here is greater than 2, then we have a modulus of continuity for D about this limiting cocycle.
Is that hard to do, or do I just take absolute values and do it?
It is not just you can prove that the Lyapunov exponent is positive if it's greater than 2. This is essentially your argument. But here we also need the modulus of continuity. You have an upper and a lower bound. And let me just write it down and then explain. So this, remember, was 0. And so this behaves like m to the power minus 2. And to answer your question, what underlies this fact is the following. If this G is large, turns out that this generates very, very regular dynamics in the sense of a dominated splitting.
Yes.
So
you have
what dominated splitting means is up to a continuous coordinate change. So what I'm saying is that if m is greater than 2, and 2 is actually optimal, you cannot improve, then if you look, you can show that this cocycle that we have up to a continuous coordinate change is a diagonal cocycle. That's what dominated splitting means. So it has this form where one entry uniformly dominates the other. So this squiggly line is a continuous coordinate change. So you can set up this coordinate change such that you have a cocycle that is diagonal with this uniform domination, and this is known to generate very regular dynamics. And then we use a cone condition, which is a technique from non-uniformly hyperbolic dynamics, to get this modulus of continuity. Yeah. And in fact, so the fact that this dominated splittings, your dynamics is very regular, is a result due to Rell from 1979, I think. So he proves that in a much more general context, that if you have a dominated splitting, then this is an open property. That's not difficult to see, I think. But then moreover, he shows that the Lyapunov exponent is infinity locally about dominated splittings, but we needed this all quantitative, so we did this analysis. Yeah. And maybe, how much time do I have left?
5 minutes, maybe?
Okay, so then I can just formulate lemma 1 also.
Sorry,
Yes,
just have a question. So
please.
When you use the fact that the derivative is in integer, so you use the fact that it exists, but when you use it,
I use it, I would need to, yeah. So the thing is that, you know, when you have a formula like this, right, and you take the right derivative, then you have clearly contributions from this term, which translates directly in this zero counting function. But then you also have contributions here. And you want to actually say that the error term does not contribute to the right derivative. And the way that this is done is to know that locally in this behavior, in the dominated splitting case, your Lyapunov exponent is smooth. In particular, the right derivative is continuous. On the other hand, in this limiting case, right, the right derivative is 0. So knowing that it is integer valued or attains valued in a discrete set is enough to conclude that you don't have contributions from there. And that's the only moment when we actually use that it is integer valued. Otherwise, yeah, so it definitely is used here because we are really computing this right derivative of the real axis. And that requires that you say that this doesn't contribute because we don't have, we wouldn't have other control of the derivative of the error term. Does this answer the? Yeah. Okay. So let me just say this avoiding zeros lemma, and that's a quantification of what Sort Spencer also had in their paper. So it's essentially, we just wanted to say that we are on this strip, right? H minus H. And so the idea is that I want to look at some substrips, delta over 2. And I want some control, I want the uniform lower bound on this substrip. So if you fix a delta less than H, what I want is that this is uniformly bounded below by something uniform in the phase, but I want no dependence of eta on this parameter. So the statement is that the height here that will be between delta over 2 and delta will depend on the value of the parameter. So the statement is there exists some eta, and the eta itself just depends on f, and of course on delta on h, such that for any e over lambda, there exists some height which depends on e over lambda, and is in here, so delta over 2 delta, so that you have this control. And then basically you put together the pieces and use this epsilon over 3 argument. Again, where lemma 3 is used to control the right derivative of the Lyapunov exponent. So this is this upper bound on the acceleration. The combination of lemma 1 and lemma 2, the modulus of continuity and this avoiding zeros, is used to prove the formula of the real axis together with the arrow term. And this is a convex function in y, which is easy to see. And then you get the result. Maybe stop here.